Up to now what we have discussed is about the ground state. We are doing only one state. Now we should switch to excited state. And for excited state, we are going to go for the example of cobalt SH4, and this is a pseudo tetrahedral complex. There is an extra P here, it should be removed with S is equal to 3 by 2. So, it has 3 unpaired electron, and the important single excitation are those which actually happens from the doubly excited to the singly occupied. The doubly occupied orbital is dz square and dx square minus y square, whereas the singly occupied T2 set, these are Eg orbital and these are the T2 orbitals. So, dxy, dxz and dyz, why they split like this? This comes from the group symmetry argument. So, you should check group symmetry of tetrahedral complexes to see why they have split like this. So, this excitation gives to 2 quadrant excited state 4T1 and 4T2, and this also helps in symmetry lowering. So, to do this kind of excited state, the easiest way is to take the d orbitals of the metal. Generally, the d orbitals of the metals are near the HOMO-LUMO. So, you can easily get to it, and you can see from the shape that they are actually d orbitals. Now, so that means I need an active space where I will put 4 total 7 electrons in 5 orbitals. That should be my complete active space. So, if I now come to the input file, so it is 7 electrons and 5 orbitals. Now, I need 10 roots. So, I am going to calculate 10 roots of multiplicity 4 and 35 roots of multiplicity 2. So, you can actually calculate more than one multiplicity at a time, because if I go back to here and if I do excitation, now if these electrons get excited and so it can lead to both doublet and quartet state. So, if one of them excitation happens with a flipping of the spin, or it can also lead to a doublet state. So, one need to calculate both the doublet and the quadruplet state in this case. So, I am going to calculate 10 roots from the multiplicity 4 and 35 for multiplicity 2, and we are going to use Ri for the trapho. For the guess, we are going to use p atom, because p atom guess generally makes sure that you get the orbitals around the HOMO-LUMO. So, valence orbitals remain your d orbitals. So, we are going to use def2 tz vp, and because CASSCF is a correlation method, we are going to need to use the /c basis set. So, let us prepare the input file. So, this is I first copied the geometry. Let me copy the input file. So, I will keep the name as this one. So let me run Orca. So it's slightly a bigger system because it contains a transition metal, so it may take some time. So now my calculation is complete. First I should open the output file using Notepad. So it will give you the basis set information, number of basis functions, number of cells, and then it says the active space. So now you see there is two blocks, block 0 and block 1. In the case 1 case multiplicity is 4, other the case the multiplicity is 2, it's doublet and quadret, and actually they are solved. So this is the initial guess, and then they are solved separately. So in all of the cases for the 20 roots and the 35 roots, 10 roots and 30 for the 10 roots and the 35 roots, they are actually calculated in a state averaged way. So for each multiplicities, for the multiplicity of quadret it's averaged over 10 state, and for the multiplicity of doublet it's averaged over 35 state, and then it's calculate the density. And it prints the transition moment. So now if I open it in Chemcraft, can go to the show TD spectrum by transition electric dipole moment. And so this is how the spectra look like. If I go to wave number unit, this is how it will look like, and the This is how the broadenings will look like. So around 20,100 the peaks are. If you want to see it in EV, it's around it's 2.5, 2.6. Here is the things what you get. So you can copy the picture and maybe I'll paste it here. So these calculations were done without the spin orbit coupling effect. And while discussing relativity, we said that it's possible to include the spin orbit coupling effect. And for the CASSCF, we will include the spin orbit coupling effect. Inside the CASSCF block, you have to give a relativity block. This relativity block does not start with percentage. The print level is 3 for the relativity, and we have to give the do SOC true. So I'll copy this input file. We save this as COSH4 SOC.inp. Just to have the convergence faster, what we can do is that I can use the MORead option. So it will read the orbitals from previously converged COSH4 GBW file. You can see that within 2 iterations it has converged. So now it's calculating the final energy. So, you can see that after your SCF is calculated, so then it will start calculating the relativistic effect by using quasi-degenerate perturbation theory. So, it will have the spin orbit mean field integrals, and basically it will solve the CASSCF first, and then it will calculate the spin orbital mean field integrals, and then rediagonalize the Hamiltonian in presence of this spin orbit mean field integrals. So, this is an way like it is an effective Hamiltonian, where the effect of the instead of considering the relativistic effect from the 0th order Hamiltonian, what you do is that you solve the Hamiltonian without the relativistic effect, and then calculate a perturbative correction for the spin orbit coupling using a quasi-degenerate perturbation theory and effective Hamiltonian. So, now it is doing the spin orbit coupling. Also calculating the quasi-degenerate perturbation theory densities. Now, I can open this one using ChemCraft. Maybe I should close the previous ChemCraft. So, now if I go to the spectra and calculate the transition dipole moment, let me go to the EV unit. If I go to the previous picture, you have just seen only two small peaks here, and if I do the broadening, you see at this portion, maybe I can just quickly increase the size a little bit, so you get to see what is there. So, there are only three small peaks here. Here you get slightly more intensities and actually get to see a slightly more height of this intensity. So, the spin orbit coupling actually changes the values a little bit more. In terms of the position, the change is not so much, but it is actually this peaks borrows a slightly higher intensities when you include the spin orbit coupling. So, let me copy this picture also. You can also do, so basically the in the case of CASSCF, you only include the non-dynamic correlation. To include the dynamic correlation, you either need to use a huge amount of CAS space, number of electrons in number of orbitals you need to increase, or you can do a perturbative or CI correction for the missing dynamic correlation. The easiest way will be to put a perturbative correction in the form of NEP-PT2, and we are going to use the strongly contracted variant of the NEP-PT2. So, the only thing you have to do is that in the same input file, you should use this keyword not in the relativity block, sorry, it has to be used outside the relativity block, and you have to give NEP-PT2 is equal to SC, that is strongly contracted. So, this will do the NEP-PT2 calculation. I have already done the calculation because it can be time consuming. So, after your CASSCF calculation is done, it will start doing the NEP-PT2. For each root, the NEP-PT2 has to be done separately. So, for the it's first doing for the multiplicity root 0, like this it will do the corrections, and after all of your corrections are done, so this is the QDPT energies. I just wanted to show you where the NEP-PT2 energies are printed. So, these are the total NEP-PT2 energies which are printed after this one, and for each root it has printed the shifts, how much is the shift in EV, and so basically this is added to the CASSCF energies and the final spectra is drawn. If I open it, this one in the ChemCraft, so steady spectrum, now of course I have to do the broadening, and if you see the peak here, maybe I should broaden it a little bit more. So, the separation between these two peaks actually gets reduced. So, they almost appear like a single peak, and the separation between these peaks, the small intensity peaks, actually increases a little bit. So, this is what you see as the effect of inclusion of dynamic correlation. You can of course use MRCI calculation to get a much more accurate inclusion of this one. So, this is a very brief overview of the CASSCF calculation. If you really want to see much more details, I suggest you to go through this CASSCF tutorial. So, this shows you this is a tutorial done by Orca developers, Daniel Arvena, Mikhail Atanasov, Vijay Chilikuri, Yang Guo, Julie Jung, Dimitrios Manganas, Bhaskar Mandal, Igor Sapiro, Kantharuvan Shivalingam, Sheng Fai and Frank Nize. These are all Orca developers. So, this is a very nice tutorial where it shows how to set up CASSCF calculation for transition metals. This tutorial you can download it from the Orca forum with the where you are downloading the Orca manual. You can see this CASSCF tutorial is there, and you can go through it line by line. So, that will give you much better idea how to do set up CASSCF for more complicated case. Now, so this is what I wanted to discuss in this course, computational quantum chemistry. So, this 12 week has been an interesting experience while trying to explain computational quantum chemistry to you. I have learned a lot of things in the process. This is not to mean this has been perfect. Performing computational chemistry calculation is like doing experiments. So, you need to have good hands, and the hands become good only with practice. So, I will encourage you to run much more calculation, ask as many questions in the Orca forum or in the mailing list for this course, and so you get a feel of yourself. And after some time, after running few calculations, you will feel confident about your result. I will again repeat, running calculation is not so much of a science, it is more of a clerical job, but interpreting the output file is science, and that is why you should spend more time, look carefully into the output file, read much more, read textbook, read Orca manual. Orca manual actually contains details about many things, so read as much as possible and try to apply computational quantum chemistry to your research problems. So, I will end it here. Thank you very much for your cooperation, and it has been pleasure to be interacting with you for last 12 weeks. Thank you.